All right, now that we have spent a little bit of time going over vectors from kind of like the pre-calculus perspective and doing things algebraically, we're going to start to look at vectors from a calculus perspective. So this video is going to be on vector-valued functions. So a vector-valued function maps real numbers onto vectors. So we're taking real points and we're just writing them as vectors. It is parametric equations that are written in vector form, and you can see that down here. This is a position vector, so if you think position, velocity, acceleration, that sort of thing. And the parametric equation has x in terms of t and y in terms of t, and so here's our vector written from a parametric equation. It represents motion along a curve, and it traces the graph of a curve. So we're going to go ahead and get started, and I think you'll realize these are not too terrible when we start to work with them. So it says to sketch the vector-valued function, and here's what it is. And we have two different ways that we can graph this. We can do it from the parametric or from the rectangular form. So we're going to say that our note to self is going to be to convert to parametric or rectangular. So that means that x equals 2 cos t, and y equals -3 sine t. And when you look at this, you might not think that it looks like a vector because it's not written in the component form, but that's because it's in the linear combination form. It's in the ai plus bj form. So it's still written as a vector. They're telling us that the values for t are from 0 to 2 pi. So if you want to use the parametric and you want to make a table and have your t values and your x values and your y values to figure out all your individual points and then graph them, you can do that. I'm going to go ahead and switch it into rectangular form because it's going to be a little bit easier to graph. So if you look at this, I remember that cos squared plus sine squared equals 1. And hopefully you've memorized that at this point, that this is kind of the trick to doing these problems because it happens repeatedly. It's not a process that is seldom used, it's a process that's pretty common. So here that means I need to isolate my cos t. And so I'm going to say that cos t is x divided by 2. For this one I need to isolate sine t, so I know that sine t is y divided by -3. And then I can go ahead and plug cos t in for cos t up here. So it's going to be x divided by 2 squared plus y divided by -3 squared equals 1. And so that gives me x squared over 4 plus y squared over 9. So this is where there's a little bit of strategy involved in graphing it in parametric versus rectangular, is if you look at this and you don't know what this is, then you can't very well graph it from the rectangular form. You might need to go back to the parametric form right here and use t values from 0 to 2 pi and use your t values to plug in and find x and find y. So this rectangular equation is an ellipse. The ellipse is centered at 0, 0. And then from the center, you go to the right and left 2. And from the center, you go up and down 3. If you were doing this from the parametric equation and you were trying to choose values for t, I would probably use 0, pi halves, pi, 3 pi halves, and 2 pi because those would be points that would be easy to plug into these equations and then also easy to graph. All right, example 2 says to change this rectangular equation into a vector-valued function. So to take it from rectangular to a vector-valued function, you have to take the rectangular form and convert it into polar form. And then once that you have the polar form, then you can just write it as a vector. So when we take things from rectangular to polar form, if you guys recall, you can just start off saying that x equals a function of t, and it can be any function of t that you want, but making it plain old t is the easiest way to go. So I'm going to say that x is t. I'm going to say y, since x is t, then y would be t squared plus 1. And so my vector valued function would be t squared plus 1, or you could write it as ti plus t squared plus 1j. All right, go ahead and flip to the next page. So vector valued functions, they use the same derivative and antiderivative rules. You just have to do the components separately, the horizontal component and the vertical component, or the x and the y. So a position vector is written as r of t, and we're going to say that the horizontal component is x of t and the vertical component is y of t. That means that the velocity vector is just the derivative of the position vector. So that's x prime of t, y prime of t. So the acceleration vector is the first derivative of the velocity vector, which is the second derivative of the position vector. So that's x double prime of t, y double prime of t. So exactly what we learned before when we were dealing with higher order derivatives, just now we have two different components. The speed is going to be the magnitude of the velocity vector. So it is the square root of x prime of t squared plus y prime of t squared. The arc length, or the total distance traveled, is the integral of the square root of x prime of t squared plus y prime of t squared. So you could say that the arc length is the same as the speed. Okay, so we're going to go ahead and make sure that we can differentiate and integrate a couple of these vector valued functions. So it says to differentiate. So if you recall that what I said earlier is it just means you have to take the derivative, but you do each component separately. So I'm going to say that r prime of t, the derivative of t, so I'm ignoring the I because that's just the notation of the vector. So the derivative of t is 1, so that's going to be 1i. And then the derivative of t squared plus 2 is 2t, so plus 2tj. Or you could write this as 1, 2t. All right, for the next one, we're going to say r prime of t. The derivative of tan is secant squared. The derivative of sine t plus 2t would be cos t plus 2. And you could write it that way, or you could say secant squared ti plus cos t plus 2j. All right, next we're going to go ahead and integrate a couple of these vector valued functions. So here we have in the I and the j form the linear combination, and so I'm just going to integrate them separately. So the integral of t is 1/2 t squared I. The integral of 3 is going to be 3t. Or you could say 1/2 t squared 3t. Now, I was being silly. I forgot one thing. This is definite, indefinite integral, so I needed my plus c on the end of those. So this would be 1/2 t squared plus c. And then this one has a different constant being added to it, so I would say 3t plus d. And then I have to fix these two. Sorry guys, didn't mean to make you erase. Okay. All right, for this one, we have a definite integral this time, so we're actually going to be evaluating this, so just remember to do these separately. So to not mess with my brain, I'm actually going to write them out separately. So the integral of t to the 1/3, I'm going to go ahead and add 1 to that, and then divide it by 4/3. So that's 3/4 t to the 4/3. And if I evaluate that at 1, that's going to give me 3/4. And if I evaluate that at 0, that's going to give me 0. So that means that my horizontal component is 3/4. And then over here, when I take the integral of this, I'm going to get ln of t plus 1. And when I evaluate that at 1, I get ln of 2. And when I evaluate that at 0, I get ln of 1. And ln of 1 is actually 0. So this would be ln 2. All right, find the position of a particle with the velocity when t equals 0 and the position is 3, -2. So I know that the position, the derivative of the position, is what gives me the velocity. That's what I know. So if I want to be able to find just the position vector, then I need to integrate both sides of this, and then I can actually find my position vector by integrating my velocity vector. So I'm going to go ahead and integrate cos 2t negative sine t. So for the first one, I'm going to go ahead and separate these out. For this one, I need to do u substitution, so I'm going to say that my u is 2t, and that means that my derivative of u is going to be 2 dt. And I do not have a 2 sitting in the front, so I'm going to go ahead and divide by 2. So I'm integrating 1/2 cos u du. And the derivative, sorry about that. The derivative of cos is sine, so that gives me 1/2 sine u plus c. That's what I've got there. And then I'm going to go ahead and take the integral of this side. So the integral of sine is negative cos, and so that's just positive cos plus d. All right, so what I have now is I have that the position vector is sine of, well, let me go ahead and say 1/2 sine of u plus c, so sine of 2t plus c, and then cos t plus d. That's what I have right now. So now I can go ahead and use the point that they gave me. They said the position vector is 3, -2. So I'm going to go ahead and solve for c and solve for d doing that. So I'm going to say that 3 equals 1/2 sine 2t plus c. And this is when t equals 0. So 2 times 0 is 0. They gave that to us in the example. They said t equals 0. So sine of 0, I'm going to go ahead and draw my little unit circle right here. I'm plugging in 0. That means that I'm plugging in 0 radians, and this is the point 1, 0. So sine of 0 is 0. So that whole part zeroes out right there, and I get 3 equals c. And then I'll go ahead and do the same for the other one. So -2 equals cos t plus d. Cos of 0 is 1, I can see that up here. Cos of 0 is 1. So I'm going to go ahead and subtract that 1 over, and I get negative 3 is d. All right, so the position of the particle is going to be given. So this was the position of the particle specifically when t was 0. Now I'm giving the general position of the particle for whatever t value you want to have. And that's going to be 1/2 sine of 2t plus 3, and then cosine of t minus 3. All right, and then we've got one last example. We'll be done. So it gives us the position of the particle where t is greater than or equal to 0. And it says find the magnitude for the velocity vector at t equals 1. So the position vector is going to be, and I'm going to rewrite this. I'm going to say this is 1/3 t minus 2 to the third plus 4, and then t squared minus 4t plus 4. So there's my vector valued function. Now they're asking me about the velocity vector, so I have to take the first derivative of this. So my velocity vector, 3 times 1/3 is just 1, times t minus 2 to the second, and this is the chain rule, so the derivative of the inside of that is just 1, plus the derivative of 4 is 0. So I was doing the chain rule, the derivative of the outside, so 3 times 1/3 is 1, times t minus 2 squared, and then times the derivative of the inside. And then over here, my derivative would be 2t minus 4. All right, so what I have here is t minus 2 squared, 2t minus 4, and we're going to go ahead and evaluate this at t equals 1. So 1 minus 2 squared is just 1, and then 2 times 1 is 2, 2 minus 4 is negative 2. So the velocity vector at t equals 1 is 1, negative 2. So now if I want to go ahead and find the magnitude of that, then I'm going to say that the magnitude of this is 1 squared plus negative 2 squared, which is the square root of 5. So that's part A. Now it says to approximate the total distance traveled from t is 0 to t is 1. And so the total distance traveled, as we said, is arc length. So the integral from 0 to 1 of, and you use the derivative of x of t and the derivative of y of t, and we already found those. They were these two things right here. So I'm going to say it's t minus 2 squared plus 2t minus 4 squared dt. And if you go ahead and plug that into your calculator, you find that the total distance traveled is 3.816 units, however many, they didn't say anything in the problem about the what the units are for this problem. All right, and then last it says, when is the particle at rest and what is the position at this time? So the particle is at rest when the velocity is 0. That's when the particle is at rest. And so that means that the horizontal component is 0 and the vertical component is 0. So I'm going to take my velocity vector and I'm going to set the horizontal component equal to 0 and the vertical component equal to 0. So for this one to solve, I'm going to go ahead and square root each side of the equation. And I get t minus 2 equals 0, so t equals 2. Over here, I have 2t equals 4, and so again, t equals 2. So it looks like the particle is at rest at t equals 2. So we answered the first part of the question. And then it says, what is the position at that time? So now I need to go back to the position vector and figure out what that is. So x of 2 is going to be 2 minus 2 to the third over 3 plus 4. So that's 0 divided by 3. So the x coordinate, or the horizontal component, is going to be 4. And then y of 2 is going to be 2 squared minus 4 times 2 plus 4. So 4 minus 8 plus 4, that's just 0. And so the position at this time is 4, 0.